Hey there, this is m253 Calculus 3, and we're diving into Chapter 2. We're in our last section, Section 2.7. In this section, we're going to take a look at cylindrical and spherical coordinates. This is going to be a similar switch that we did when we studied polar coordinates, except this time it's going to be in 3 dimensions. So what's the difference between cylindrical and spherical coordinates? A cylindrical coordinate, would be able to describe a cylinder quite easily. So cylindrical coordinates will have the same representation as polar coordinates, with x is equal to r cosine theta, y is equal to r sine theta. But then we're going to keep z as a third variable by itself, z going up. So imagine being able to create the circles or those polar coordinate graphs, and circles being a really important part of polar coordinate graphing systems. And the circle on the xy plane would just get swept along the z-axis, and you have yourself your standard looking cylinder. We can also think of this as cylinders if your shape is any other shape in the two-dimensional domain, and then we sweep it up and down so the rulings would still be parallel to the z-axis. And then there's other relations that's going to be important for us. Same relation where r squared is equal to x squared plus y squared, and then tangent of theta is equal to y over x, and then z is still equal to z. And so you can see the picture that describes a point in Cartesian coordinates x, y, z to a point in I was going to say polar, but it's in cylindrical coordinates, because now you not only have an r and a theta, but you also have a z attached to it, because now it's in 3 dimensions, and now it's in cylindrical coordinates. Now, spherical coordinates gives us a way to describe a sphere natively using the coordinate system. And in this case, we're going to introduce a few new variables. We're going to introduce the Greek letter rho. It looks like a P, but it's actually an R in Greek, the Greek alphabet. But the Greek letter rho will describe a radial distance from the origin to some point in 3-dimensional space. And so with that, we can think about rho as a distance, or rho is equal to the square root of x squared plus y squared plus z squared. Or if we square both sides, rho squared is equal to x squared plus y squared plus z squared. So that's rho. Theta is going to be the same theta that we've used in polar coordinates and also in cylindrical coordinates. That's the two-dimensional angle on the xy plane from the positive x-axis going counterclockwise. And now the other new variable that we're going to introduce is phi. That's a Greek letter phi. That's going to be an angle measurement from the positive z-axis going down. So in general, we want that angle going down. We're not going to go past the negative z-axis. So we generally want our phi to just go from 0 to pi, no more than pi. If we let our phi go from 0 to pi over 2, then we're only going to cover the top half of our space. So the first 4 octants that's above the xy plane, where z is positive. And if we go from pi over 2 to pi, then we're going to get the bottom half of that. And so that's how we're going to get our measurements. The very important transformation that we're going to need to remember is going to be x is equal to rho times sine phi times cosine theta, and y is going to be rho times sine phi times sine theta, and z is going to be rho times cosine phi. Now, this relationship between x, y, z and rho, phi, and theta can be derived by taking advantage of our polar or cylindrical coordinates. In that, if we take a look at that measurement, if we take a look at r as that same r variable from polar or from cylindrical coordinates, then we can find a relationship between r and then rho and phi. So it turns out that with that relationship, it's hard to look at it just by looking at this picture, but if you actually draw on this picture, you can see that r is going to be rho times sine phi, and r is going to be, if r is rho times sine phi, then we can look at x as r cosine theta and replace r with rho times sine phi, and then you're going to get the relationship in cylindrical coordinates. The other relationship equation that they have here is that phi is going to be equal to the arc cosine of z divided by essentially z divided by rho. But rho is equal to square root of x squared plus y squared plus z squared, so that is how it's expressed. In any case, now we have a way to easily represent spheres with the spherical coordinate system, and we'll take advantage of that a great deal in later on in chapter 5 when we start dealing with triple integrals, and where you need to describe parts of a solid that is described by a sphere. Okay, so that wraps up our chapter 2. With that, we're ready to put all this stuff together, all the vectors, the dot and cross products, lines and planes, and then all these surfaces with quadric surfaces and spherical and cylindrical coordinates. Okay, good luck.